Hi, in this video we finish our A-star search algorithm. I'm going to create two classes. The first is going to be the core of the algorithm, so I'm going to name it algorithm. And we will need a class from which we are going to test it. So it is an app with the main method, of course. And here we will have a public void A-star search method. It's going to have a node, source node. It's going to have a goal node, goal node. It's going to be the final destination. And we have to use a priority queue, as I said earlier, for the nodes. It's going to be the unexplored nodes queue. Equals to new priority queue. Okay. So we keep pushing and adding these nodes to this unexplored nodes queue, and we keep adding the neighbors of the given node we are currently at. And it is good because a priority queue, with the help of a heap, we can extract the minimum element in logarithmic time complexity, as I said earlier, because in order to get the minimum, it is constant time, and we have to rearrange and update the heap, and it takes logarithmic time complexity, and in the overall time complexity will be logarithmic, of course. So this is why it's very important to be familiar with these priority queues and heaps and abstract data types and data structures to know what data structure to use for a given problem. So the source node that set G score is 0. It is equal that we set the minimum distance when we were implementing the Dijkstra's algorithm, because the G score is the same as the min distance. So the unexplored nodes queue that add, we keep adding the source node, and we have a boolean is found equal to false, and we keep iterating while the unexplored nodes queue is not empty and we haven't found what we are looking for. So not is found. So we have a current node equals to unexplored nodes dot poll. We have a explore node. Oh, I'm going to create a public list node. It's going to be the explore nodes list, or explore nodes for sake of simplicity. I'm going to initialize it. This dot explore nodes equal to new array list, of course. I imported the list, java.util.list. So this, or maybe it would be better, I'm leaving this. I'm going to create a set. I'm going to create a set for the explored nodes. So it's going to be a set node explore nodes equals to new hash set. Okay, explored nodes, and we keep storing the explored nodes in a set data type, data structure, sorry. So at the current node, so we explored nodes that add the current node, and if the current node that get value that equals to the goal node that get value, which means that we get to the node, the goal node, and we are standing there. I think we are missing, yeah. So if it's the goal node that I said the is found equals to true, and it's important because unless if it's false, that we keep iterating this while loop forever. So, and we keep iterating through the edges as we have done with Dijkstra's algorithm. So the current node that get adjacency list, and I'm going to have a node, child node, it's equal to E that get target node. I'm going to have a double cost, it is the cost of the edge. I'm going to have a double temp g-score is equal to the current node that get score plus the cost, and we have a double temp f score which is equal to the temp g score plus the heuristic of the child node and the goal node. And this is very important because this is where the Manhattan distance came to play, which means that I'm going to define a method that's going to return a double. And but anyways, I'm going on with my A-star algorithm, and later on I'm going to explain why I did the things I did. So okay, if that explored nodes that contains the child node and the temp f score is greater or equal to the child node that get f score. Here we just keep checking whether it is there any better solution. So the temp f score, which is the overall, the sum of the g score and the heuristic, if it's greater than the child node and the explorer nodes contains the child node, then we just continue because it's not a good solution. And else if the not unexplored nodes queue that contains, so if this queue doesn't contain the child node, or the temp f score is less than the child node that get f score, then we know that it is a better solution. So the child node, we set the parameters of the child node, set parent node to the current node. We set that child node that set g score equals to temp g score, of course, and we set the child node that set f score, the temp f score, of course, and if the unexplored, the queue that contains the child node, then the unexplored, that we have to remove this child and we have to add it to again with the updated parameters. So unexplored nodes that add child node. It is, if you can recall, it's basically almost the same as for Dijkstra's algorithm. We just have to check, iterate through the edges, check whether there's a better solution and we keep checking whether this temp f score it can formulate a better solution, but it is different because we have an additional parameter, that heuristic, and this heuristic is the so-called Manhattan heuristic. And I just have to return. It is a definition. It has nothing to do with me. This Manhattan heuristic was created by mathematicians, physicists, computer scientists. So I think we just have to take it for granted. It is a bit different than the Euclidean distance. We have to, at least I'm making the formula, and later on I'm going to talk about it. So it's a node 1, it's a node 2, so the get x minus node 2 dot get x plus, not there, plus math that apps node 1 that get y minus node 2 that get y. So if you write it out several times, I think you are definitely get the grasp of it. Then we just have to check the distance on the x-axis between my position and the goal position, the destination node I'm heading for. What's the difference in the x-axis and what's the difference in the y-axis? I had to add the two, and this is the Manhattan heuristic. I think it's nothing special about it. We just have to take it for granted. That's all. In the next video, we are going to test our A-star search algorithm. Thanks for watching.